Good afternoon, everyone. Welcome to first day of STTP in session 2, organized by Saraswati Institute of Technology, Kharghar. It's my pleasure and honor to introduce our today's speaker, Dr. Vinay Nikam sir. Dr. Nikam sir is the director of Urban Hydro Environment Center and has 25 plus years of experience with the various organizations. He is currently working on research project related to development of real-time flood forecast model and geopathic stress identification and mitigation. He is high-level expert committee member to study the effect of climate change on rainfall and urban drainage system and suggest the measures for the mitigation of floods in Mumbai city in future. He is invited for paper presentation in India UK Water Center workshop on science and innovation for catchment management. He is also involved as a research associate with IIT Bombay on international collaborative research on flood resilience of urban areas project under FP7 program of European Union. He was awarded first prize winner of National Concrete Cube Testing Competition in 1995 conducted by Indian chapter of American Concrete Institute and Best Paper of the Year award by Indian Water Works Association. He is sponsored by the Ministry of Environment and Forest for the Thane Municipal Corporation for pursuing the MTech. Now, I would like to hand over this session to our today's speaker, Dr. Vinay Nikam, sir. Sir, please.
Yeah. Uh, Namaskar and good afternoon, all of you. The most welcome to this 5 days short-term training program on the environmental engineering for the global sustainability. Thank you, madam, for a nice introduction. And so I would like to thanks to the Saraswati Institute of Technology for giving me an opportunity to present a topic on the climate change and urban flooding. Of course, the every monsoon, now it's a monsoon period is going on, and we see some other places the flooding is going on. So let's understand the impact, how the climate change is impacting on the urban flooding, what is its impact, and really whether it's happening, the climate change is happening or not. Okay, because there is a lot of debates are happening, the pros and cons of the climate change on the urban flooding. So let's have a walk through for the next 1.5 hours or 2 hours through the presentation, right? So first of all, I would like to thanks all my gurus for teaching me, all my spiritual gurus, all my teachers and the professors for making me happen. Okay, at this stage. Okay, so Guru Brahma, Guru Vishnu, Guru Devo Maheshwara, Guru Sakshat Parabrahma, Tasmai Shri Guru Namaha. So without Guru we are nothing. Like without teachers we are nothing. So a lot of heartily thanks to all my gurus, all my professors. So with this we start our presentation. So a lot of the news happening even in the last 6 months or 1 year that in a present day warming, the temperature is increasing by 1.5 degrees. And this is a very recent reports of the Working Committee 6, which is presently which is recent published. And if you see the India scenario, so there almost it has been shown that the temperature rise will be in tune of 1.5 to 2 degrees. Okay. Now there is a task how to reduce the temperature. Okay. So my learned, very senior friend of mine, and is a colleague, and he will of course within 2 days he will give the how we can reduce the emissions from the residential buildings for the infrastructure projects, and how we can mitigate, how we can reduce the rise in temperature. Okay, so that is a special topic which will be covered by the Mr. Vijay Kulkarni. Okay, because we both are working on the same field, same area. Of course, I'm looking for the flooding, and he's looking after the infrastructures and the residential projects and other things. So he will, and we do represent in low carbon construct forum. So we will take much care in detail about how in infrastructure projects we can reduce the rise in temperature. Okay. So, in a nutshell, there is an increase in temperature because of the global warming by 1.5 degrees Celsius, right? And this is a evaluation for over a period of the years from 1860 to 2020. So, over a period of the time the temperature is increasing because of the greenhouse gases emissions, right? So, what are the possible mechanism for the urban induced rainfall modifications? Okay, now we understand because of the climate change, we have witnessed that there is an increased number of a high intensity rainfall, right? So why this is happening? So one is because of the uh, atmospheric destabilization through the enhanced low level heating. It is called as a commonly called as a known as a urban heat island effect, okay, which is prominently observed in the urban areas and the adjoining areas. So increased low level convergence due to the surface roughness, then the modification of the microphysical and the dynamic processes, and the modification of the low level atmospheric moisture content, and the pollution from the automobiles and industry. Even if you say the case of the Mumbai, India, right? We have frequently seen the cyclones happening on the east coast, right? Cyclones happening most prominently on the east coast. But now, even from the last 2 years, we have seen even the cyclones are happening on the west coast. Okay, this is mainly because of the climate change, because of the rainfall effect, and because of the urban heat island effect, high intensity rainfall has been observed not only for the city area but adjoining areas to the cities. Okay, now what is happening because of the urban heat island effect? The day and night temperatures, the difference earlier, it was a huge difference, maybe in tune of 5 degrees or 7 degrees or 8 degrees. Now the difference has been getting reduced because of the urban heat island effect, right? Even I've done some studies where I've checked the Mumbai temperature, then the Delhi temperature. So even we have seen that the difference, earlier difference was 8 degrees Celsius. Now it is only 4 degrees Celsius. So that's why we feel very uncomfortable even by the 10 p.m., the 11 p.m., the 12 p.m. in the night, right? Even after 12 p.m., the difference increases, but up to the 12 p.m., that the difference between the day and night temperatures are much less. That's why we do feel the very uncomfortable scenario, right? So same is the case of the Shanghai. Then if you see the Asian countries, the Tokyo, Seoul, Shanghai, Beijing, the difference between the day and night temperatures is getting reduced because of the urban heat island effect. So these are the diurnal variations of the surface heat island in the East Asian temperature cities in the summer. This the first one is Tokyo. Then the Beijing daytime, the Tokyo nighttime, and the Beijing nighttime. So if you see even the nighttime, the temperature is high in the both in the Tokyo and the Beijing, right? Similar Shanghai, the daytime and the nighttime, you see even the nighttime temperature is very high. The Seoul also same thing. The nighttime temperature is high. It is because of the reflection of a heat from that is absorbed heat from the building surface. And if you see the Shanghai and the Seoul and other, they have got a very high rise structure. So because of the high rise structures, emit the uh, heat. Okay. The same is the case of the Bangkok, Manila, SCMCT. Then the impact of the climate change are the two. The first, if we have seen the very high intensity, very short term, very high intensity rainfall. Okay, and another is the sea level rise. Okay, so lot of news that sea level rise will be happening, and even in the Mumbai there will be lot of sea level rise. So, and this has been documented in the IPCC sixth assessment report, that's the AR6, which is very recently published. That's published in last year itself. Okay, so there they have given the this is a very good website where they have given the at various locations of the world what will be sea level rise. So if anyone wants to understand what will be the sea level rise for the different scenarios, of course they have worked out for the different scenarios. For an example, SPS 7.0, SPS 8.5, with a low confidence, with a high confidence, what is the average. So the below this image shows the for the all scenarios. Okay, so if you see the most possible scenario for the Mumbai, that's the Apollo Bandar. So they have estimated that what the sea level rise will be 0.58 meter, which is very much alarming, right? Uh, and whether it is will really happen, let's see, because this is a 0.58 is after 100 years, right? So, but there are several estimates by NERI as well. But even in the uh, last report at the AR5, they are also given some estimates, right? That what will be the sea level rise. So it is one known thing that there will be double impact. There will be the sea level rise, and at the same time there will be high intensity rainfall. Okay, short term high intensity rainfall. So that's what is happening. If you most of the time, if you see that within a 15 minutes, that now the what is happening, that the rain spills within 15 minutes, there's a high large amount of rainfall happens, right? This is a high intensity, and this high intensity rainfall is very much crucial for the urban areas, which is very much crucial for the flooding point of view. So this, if you remember, this figure is a 0.5. It is a recent figures of the AR6. And if you refer to the CPHEO manual, for your information, earlier, before 2019, there was no manual for the stormwater drain. No, what I mean to say is that is no dedicated stormwater drain manual. Okay, but in year 2019, the separate manual was published, especially for the design of the stormwater drains. But earlier there was only the 5 to 6 pages, which was covered into that to the sewerage manual, which we used to take care of the design of the stormwater drains. Okay, and this new manual, they have specifically mentioned that what will be the water sea level rise. Okay, so they have mentioned that the sea level rise will be between the 3 centimeters to the 10 centimeters per decade. It means, what if you see the for the 10 years period, for the 100 years period, is a 30 centimeters to the 100 centimeters, right? So it is varying from the 0.3 to the 1 meters. So this is basically based on the AR5, that's the earlier reports, right? Then in the manual, because why I'm referring the manual, because manual has given the earlier IPCC reports findings, right? Now the present, it is much more, it is double than as compared to the earlier one. But since for the planning per se, we have to follow the CPHA manual, and one should understand what has been mentioned in the CPHA manual, because what I've seen from the field experience, that many of the practitioners, even they don't know there is a CPHA manual exists, right? So this is a state of art. So that's why I'm very much clearly specifying here that the CPHA manual is there for the design of the stormwater drain, and where they have specifically mentioned that the rise in mean sea level along the Bay of Bengal will be 1.92 millimeter per year, right? So and for as far as the Arabian Sea is concerned, it is a 1.72 millimeter per year. That means if you multiply by the 100, it will be of after 100 years, right? So these numbers we have to consider for designing of the coastal cities. Another thing is that they have also given the very nice table where they mentioned that for the effect of the climate change, we have to consider the rise in sea level by 0.3. So mind it, when we are designing the coastal areas, the coastal stormwater drain for the coastal cities, so we have to take this rise in sea level by the 0.3, and accordingly we have to design not only the drain invert levels but also the formation levels of the plot. At the end, I'll be covering some case studies, because without so we will understand how we have to consider the impact of the climate change, right? So these are the recommendations of the CPHU manual. And let's understand the urban definitions, right? So this definition is being given by the Ministry of the Urban Development side, and the small towns having the population of 5,000 to 20,000 is designated as small towns. Then the small town 2 is a 20,000 to 50,000. Medium towns, again, they're classified into medium town 1 and 2 based on the population. And metropolitan cities has been defined as having the population of 10 lakhs to the 50 lakhs, and the metropolitan 2 cities, that's a 50 lakhs to the 1 crore. And the megapolis is a more than 1 crore. So this is a definition of the urban settlements. Then let's understand how this urban development is happening, is affecting the runoff. This is the most common figure, but I will, to maintain the continuity of the presentation, I will explain what is happening because of the urbanization. And if you see, the most of the time, most of the places, the development has been taken in the low-lying areas, because that's the only space which is available presently for the development in the urban areas, right? So even I have been visiting so many places, so many metro cities, and for an example, Chennai, majorly most of the places are the low-lying areas. If you see, even from the flight, you can see the Chennai, there are a lot of waterlogged areas, and this is because of the low-lying areas. There's several low-lying areas. Bangalore, there are several lakes which has been now converted into for the habitation. By Bangalore, or even if you think of Hyderabad also, there used to be so many lakes, and now the so many lakes are being encroached by for the development purpose, right? So there is a modification in the hydrology of the region because of the development in the low-lying areas and the construction of the buildings, the car parks, pavements, the concrete roads. So because of this, there is a lot of impervious areas are getting reduced, and the natural filtration which used to happen earlier, now it is not, the rainwater is not getting infiltrated. So that's why most of the rainfall is getting converted into runoff, okay, and that's why the runoff volume is getting increased. So if you see here, because of the before the development, the time to peak, what I mean to say, the time to peak, that is the farthest point from the point of the disposal, a point of the interest. So that time used to take 30 minutes, but because of the urbanization, now that within a 20 minutes water is reaching to the point of location, point of interest place, okay. So this is very much crucial, right? So this is one of the main reasons for happening the floods in the urban areas, because there is no infiltration in the soil, there is no obstruction to the or no detention to the runoff. So that's why everything whatever is happening is getting converted into runoff within a short span. And this short span conversion of runoff for runoff is a very much dangerous, right? So this is something, a point of interest which we has to be taken care, right? Then let's understand the various factors affecting the flooding, right? So one is extreme rainfall, which is happening. That's the meteorological factors. If you take the case of the 26 July 2005, there's a 944 millimeter of rainfall in a single day, and that too a 190 millimeter of the rainfall in a 1 hour. So it's a very extreme. That is called as a very, very, very extreme event. Okay. Then cyclonic storms, the climate change. The climate change, the impact is a short duration, high intensity rainfall, right? Then the another hydrological factors such as high tide impeding the drainage, right? So what is happening in the coastal areas? What is happening in the Mumbai? What is happening in the Chennai or other coastal areas? Whenever there is a high intensity rainfall, and if it is coincide with a high tide, there is the flooding happens, so the waterlogging happens in the city area, right? So Mumbai is working on that directions, how the impact can be reduced. So then the absence of the drain network. And some places there is absolutely no drain networks. I have been to the Hyderabad very recently, the last 15 days, and the very big IT area. I was surprised there is no drain network, right? So what will happen? So if there is no drain network, Even the new areas in the Hyderabad, cyber city, Cyberabad, there is no drain network, right? Roadside drain network, I mean to say. So in that case, what will happen? So roads will act as a drain. Okay. Sometimes long back in an international conference, one of our partners from the Europe, they said, okay, there also the roads are acting as a drain. So that it was their okay. Their countries, the rainfall is not much. Okay, so it's allowed. Okay, road can be act as a drain, but can we afford in India? Because here we received a very high rainfall. Okay, during the monsoon period, we can't afford that our roads are acting as a drain, right? But this is what is happening. That's why you see the 1 feet, 1 feet, 1.5 feet, or 9 inches of water on the roads, right? Because of the absence of the drain network. Then the channel crosses the cross-sectional shapes and the roughness. This is a more many places I've seen that the cross-sectional areas has been reduced. Even the shape also matters. And the roughness are increased because of the lot of the siltation, lot of the what I mean to say, the roughness is a Manning's coefficient of roughness, right? So if it's a smooth, it's a 0.015. But if it's a silted, if it's a lot of vegetation, then the roughness increases. And once the roughness increases, the capacity of the channel gets reduced. Okay, so that's one of the factors for affecting the flooding, right? Then the culverts. So most of the time, the culverts should be properly designed. At least should be designed for the 1.5 times, right, the size. But most of the times it is almost same as a width of the channel. But actually it should be 1.5 times at the uh, size of the drain. Okay. Then the natural surface infiltration rate, change in runoff coefficient, is a lot of this is we have seen because of the urbanization, the siltation and the drains. Okay, if both this is mostly commonly observed in the where the channel slope is very much less, and the channel slope is very much less because of the if you take a case of the coastal areas, of course we get a very because of the flat land. With the flat land, then the drain velocity, then the drain slope gets reduced. And because of the lesser slope, lesser slope results the lesser velocity, and because of the velocity is less, there is a siltation in the drains, right? Then the dam overflows. The dam overflows is also the main cause of the flooding, right? So what happened in the 26 July 2005? There was a dam overflows for Bihar dam overflow and the Pervi dam overflow. So there's a combination of all. Then the human factors are the land use change. That's the increase in runoff, right? So construction in the floodplain, which is very much happening. If you see the past, if you see the here, this is a uh, image of the Thane Creek, right? So this is a 2000 image. So there was not much development. And if you see the 2020 development, and if in year 2000, this open areas was actually acting as a holding ponds, right? So and holding ponds before the Thane Creek, and it was actually acting as a buffer for the cities, right? But in 2002, 2020, we have seen if we have a lot of slums settlements in the open areas, then the organized development, residential development. And because of this, what happened? Because of this, the your holding areas gets reduced, right? If the holding area got reduced, then what will happen? It will result the flooding on the upstream areas, right? So how to tackle this? Because how to tackle the, and in addition to that, there will be a rise in sea level, right? So if we take the case of the Thane Creek, so because of the sea level, there will be rise in zero point 0.3, and at the same time your the open areas already developed. That how to take care. So that also I will explain how to take care in one of the case study, right? But one should aware, because what happened that designer, most of the drains, the earlier drains are not designed for the rise in sea levels. Even they have not designed for the impact of the tidals, right? So because they are the old designed by the old school of thoughts or old methodologies. And this I will explain in the very coming slide, right? What is happening. Siltation and the inadequate cleaning of the nala, which is we have seen the every year. But as per the NDMA, that's a National Disaster Management Authority guidelines, because they have published a very nice guidelines long back in, I think, 2009, where they have mentioned that the all urban drains should be clean at the end of the March itself. Okay, but you most of the time, if you have seen the even in the May end, they are doing the cleaning up jobs. Okay, then the blockage of nala waterways, culverts by the solid waste. This is most commonly we have seen, because the drains are also not only acting as a channel for the for the wastewater, but also acting as a disposal place for the solid waste, right? So this is definitely, by disposal of the solid waste, it do block the the culvert. So this figure shows the very huge solid waste deposition at the entrance of the culvert itself. Okay. Then the inadequate inlet arrangements. So many of the time, what I have seen, that there is no proper inlet arrangement to the drains. Okay, because of this, there is a lot of water accumulation on the roads. Then the sudden release of the water from the dams. What happened in the in a Chennai, there was a sudden release of the water from the dams, because if it's properly regulated, then everything problem will get solved. But it's not, the overflow flows of the dams are not properly regulated most of the times. Okay, so then the inadequate inlet arrangements of the adjoining drain to the nala. I have seen so many nalas, the drains, the bigger drains, the rivers, and what I have seen, that in this, if this is a main drain or the river or the canal or the nala, so they adjoining areas, stormwater drain, they connect like this. Okay, in a right angle. So mind it, how the water from these adjoining areas will enter into this drain. So definitely, if it's not water entering into this drain, it will result the water logging on the back, right? So ideally, it has to be disposed into. Even in some places, I've seen the inlets are like this. So in opposite direction, right? So this water will not allow this water from the adjoining areas to enter into the drain. So these are the something factors, human factors, which affects the flooding, right? So let's understand the design factors, okay? Because uh, many of the urban stormwater drains has been designed by the old CPHU manual, right? And for your information, the Amrit projects, that's a Amrit project, and the Jawaharlal Nehru National Urban Renewal Mission projects. So in year 2006 to 2011, lot of cities, the projects, many cities, many cities, the stormwater drain has been constructed based on the CPHU manual. Okay, under the Jawaharlal Nehru National Urban Renewal Mission projects. Even after that, in the last 5 years, in the Amrit mission, that's Amrit mission, also stormwater drain has been designed, and this has been designed based on the old CPHU manual. Why I'm referring all these things? Because you should aware that why the urban areas are getting flooded. Okay, and the next part is the climate change, of course. But apart from climate change, because of the improper design, the flooding is happening, and the climate change is adding to it. Okay, then the lower return period, in the last CPHU manual, it has been mentioned that return period should be of 1 in 2 years, or some places is it 2 in 1 years. What is mean by the 1 in 2 years? 1 in 2 years means what? Means you are allowing to flood once in 2 years, right? But in a present manual, as per the present manual, it has been revised to the 1 in 5 years, right? And it should be 1 in 5 years at least. So then the non-consideration of the tidal impacts. I have seen various stormwater drain design reports of the various municipal corporations, right? So they are designed by using the simple spreadsheets, right? And how the simple spreadsheet will take into account of the tidal impact? It will not, because in a simple spreadsheet, it's only from node to node. For the tidal impact, we have to do the modeling, right? So all the earlier designs, they have not considered the tidal impact. In addition to that, they have not at all considered the climate change factor for the rainfall. So mind it. So whatever happened earlier, they have not considered the tidal impact, they have not considered the climate change impact, and the drains are already constructed. Then this is a study which has been done by my guide, my professor Kapil Gupta, and which was published in one of the journal. So these are the statistics of various cities across the India. So where we have seen the very high rainfall, right? So which is exceeding the 50 millimeter per day. So this is an open question to all. Are the current policy planning implementation mechanism for the urban flood management effective within the context of the climate change? If not, what changes need to be made to address the problem posed by the climate change? Now we understood that the urban stormwater drain are not planned for climate change, right? Then what should be done? This is why. What are the major issues that the political, social, economical, financial, and environmental likely to have a significant impact on the urban flood management in the changing climate? See, for the Mumbai, the Brimstone report was published in 1992, right? Which has clearly given its recommendations, right? But there they have mentioned some rainfall intensity which should be considered. Even after 2005, Chitle committee said so and so rainfall intensity. For an example, 100 millimeter per hour rainfall intensity should be considered. Okay. Now, earlier Mumbai, it has been designed for the 25 millimeter per hour rainfall intensity by the British period. Because why 25 millimeters? Because in the London, the maximum rainfall was at 25. Because it has been designed by the British period, British designs, right? Mumbai stormwater there. So same formula, same they have applied for the Mumbai. So that's why they have designed for the 25 millimeter per hour. Okay, this is the background of why Mumbai adopted the 25. Then, as per the Brimstone recommendations, now they are revising for they are augmenting the existing to the 55 millimeter per hour. But having said that, the major critical infrastructure should have to be designed for the 100 millimeter per hour, right? But it's not designed for that because because of what? Because of the financial constraint. Because they don't have that much budget. Because that was even not only the Mumbai Municipal Corporation, but for the several organizations, right? Several local authorities. When we do check their design stormwater drains, then and we do suggest that okay, you should design for so and so rainfall intensity. But then the second question they ask again the query, okay, we can design, then widening the cost, then it increases the cost of the DPR, then the encroachments adjoining to the areas, right? So because of all these factors, because widening of the drain, it requires again the several permissions, and if there's a slum settlement, then again there is political involvement into that, then there's social involvement into that, then economic involvement into that, then the financial impact of the resettlement of that. So because of this are the several impact factors which constrain the augmentation of the drain in the urban areas, and ultimately to the climate change. Because the climate change impact, to understand the climate change impact, we have to widen the drains. There is no other options. Of course, there is an option we'll discuss later on, because there is an option. Because engineers, if they say there is no option, there is no this, then he's not an engineer, right? So engineering, there are options are there. Maybe the cost is which is being implemented worldwide, because it has happened. It has happened because existing drains are done. There is no space. There's no space to widen. Then what should be done? Okay. So that's why the meaning I will explain with a case study with a nice video how the developed countries has been doing, right? So then is it possible to identify the both important synergies and the significant impediments? That is, will adapting the urban flood management principles and techniques to the climate change make other problem worse or better? Okay. So this is some of the open questions. So if you see the major metro cities, the Hyderabad, the flooding events are happening in 1954, 1970, 2000, 2001, 2002, 2006, 2008, even now it's happening. So the frequency of the flooding has been increased and there are huge losses. Delhi, there is a frequent flooding because of the Yamuna River overflows, okay? And the loss is also very high. Then the Chennai have been working for the several projects in the Chennai for the flood risk assessment. And what is as in that the frequency of the floods in the Chennai is almost 1 in 5 years, right? So at least the drain should be designed for the 1 in 5 years. But if we follow the older, because already the constructed drains, they are designed for the 1 in 2 years return period, so we can't help that. But at least for the new drains, it should be designed for the 1 in 5 years, because we have witnessed the frequency of the flood 1 in 5 years, right? So in Chennai 2015, the mega floods were witnessed in the November and December, and especially in the December 3rd to 5th December, right? Bengaluru, so there is a flooding, severe flooding happened in 2005. That is a 525 millimeter in 24 hours. Okay, that's a huge, right? Huge 525, and this is why this is one of the reason of the climate change. In 2009, 2013, 2016, so every place is the impact. So how the movement of the water is happening in the urban areas. So if you see the precipitations and it is falling on the stormwater, converting the stormwater runoff from the urban catchment areas, and it is mixed with the traffic, road traffic pollution, then the sediment load from the soil erosion, then the urban wastes, right? So this is getting converted in the urban surface runoff. Okay, and then if you see the surface and the groundwater abstraction from the water supply systems, the domestic wastewater, industrial wastewater, other used waters, and the urban wastewater. Now, again, we used to discuss, myself and my professor used to discuss several times in the IIT Bombay. What is happening? The drains which the open drains are now acting as a for the both as a combined sewer, right? So it's the case of the Mumbai or everywhere the channels are acting as a disposal for the sewer line. So it's basically a combined. So this and during the monsoon, what is happening? During the monsoon, we do open the sewer lines. Okay, so it is very common practice in the Mumbai, right? So we do open the manhole of the sewer line. So we allow the rainwater to enter into the sewers, right? And finally, where it will go? It will go to the pumping STP, right? So this is something ulta case, right? Which is happening. So we are converting the open channels into the sewers, and during the monsoon, we are converting the sewer line into the stormwater drains, right? So this the stormwater drain system, the sources, the BMP measures which will covered definitely, and the untreated discharge which is going on. So this is then the of course during the summer, during the monsoon, some systems are acting as a combined sewer systems. Okay, and even because I've seen the culverts, I've seen the drains and all. Even during the non-monsoon period, they are almost full, right? So if you see during the non-monsoon period, they're almost full. What will happen during the monsoon period? Where this water, how the water will get accumulated? Okay, the water will not accumulate because already there is a sewage, the huge sewage into the wastewater into the open drains or the drains or into the nalas, right? Okay, so let's see the how because how the drains are designed. Okay, so drains are basically there is one a very good formula. This rational method. So rational method is a function of the coefficient of runoff, then the average rainfall intensity. Average rainfall intensity. mm, that's not average, should be a peak rainfall intensity for the specified time of concentration, and A is area, right? Why I mentioned here, because we have to understand how this formula is impacting uh, the drains design, right? And And this formula has been also specified by the CPHEO manual, and proper understanding of this rational formula is very, very, very much important. Because even if you understand, because of the climate change, there is a high intensity rainfall, and because of the tidal, there will be rise in, because of the sea level, because there will be the because of climate change, there will be rise in sea level. So yes, we do both things are understood, but how to incorporate, right? And most of the times, what most of the designers they forget the time of concentration, even if they do understand the time of concentration properly, but they do mistakes in a designs. How? Then these are the coefficient. Let's understand how they do mistakes, because of course we are learning from the mistakes, but mistakes should not be repeated. That's the main thing, right? Because why I'm mentioning, because many a lot of faculties are attending this uh, lecture, right? And see, we do teach the rational method, but it should be taught in a proper way, right? And the books, because I have, even in the colleges, I learned in a college, okay, Q equal to CIA. This is very common formula, right? So the books are so we have to pick up the proper formulas from the book, and the supporting information which is required for the formula, right? So what is happening? The coefficient of runoff. This is the coefficient of runoff is specified by the CPHO manual. Okay. Uh, but we have to, okay, for the commercial areas is 0.7 to 0.95, industrial areas is zero point 0.6 to 0.9, but and residential areas are zero point 0.6 to 0.975. But from my practical experience, I most of the time, or not most of the time, I maximum use the coefficient of runoff as a 1. Even when the Mumbai Municipal Corporation, they have recommended that coefficient of runoff should be a 1. Because why? Because why? Even the Thane Municipal Corporation, they recommend the coefficient of runoff should be a 1, not only for the paved areas, but also for the garden areas. Why? Because once the soil is saturated, then everything is runoff, right? Whether it will absorb, it will not absorb much. So in case, so even in case of the peak, that everything will be a runoff getting converted into runoff. So which is advisable to have to adopt the maximum coefficient of runoff. This is a 1. Okay. But this is a provision of the present present CPHU manual, which is published in the year 2019. So the design after 2019, they will follow this coefficient of runoff, right? But earlier manual, the coefficient of runoff used to vary with the time of concentration. Now I would like to explain here, because the coefficient of runoff is a function of the surface area. That I think that much clear, right? So if this is a your ground, okay, it's a totally paved area, whether the coefficient of runoff, that is a property of this particular ground or top surface, whether it will vary with the time of concentration. No, it can't vary, right? Because it will remain the same. But this was specified in the earlier CPHU manual. The time with the varying time of concentration, the coefficient of runoff will change. And mind it, with this design methodology, all stormwater drains in the urban areas has been designed. So now you must be wondering, oh, why this flooding is happening? The flooding is happening. This is one of the main reasons, because they have designed for the lower coefficient of runoff considering the time of concentration. This I will explain here. Okay, so if any particular area, the time of concentration, duration is the time of concentration. So if it's 180, then coefficient of runoff is a 0.85. But at some particular places, the coefficient, if the time of concentration is a 0.3, so coefficient of runoff is a 0.65. This is not a practical case, right? So practical case. So if this is soil is a paved area, it will remain 0.9. How? It will not vary with the time of concentration, right? So but in practically, but all the designs has been this with this concept, right? So basically they are under designed. And then I have put a lot of efforts in understanding from where this has come. Okay, because uh, my professor was on the committee of the CPHU manual. When she has drafted the he was the committee member for the chapter 3 and 5 of the CPHU manual, and we've gone through the so many manuals, so many literature. So from where this, because we anyway we wanted to remove this table, right, from the CPHU manual, right? Because it was earlier it was included, so they wanted to CPHU people, they wanted to include in this manual as well. But we said no, this is very wrong concept and this has to be removed, right? So we actually made a lot of search from where this figure has been came, where this horn, from where this honor has came. Basically there's a honor. Honor is a scientist which was carried out some experiments in the 1910. 1910, that is also for the all the non-urbanized area, that's the agricultural areas, and where he has developed some of the formulas, some of the correlations, and where he has mentioned that coefficient of runoff is a function of the time of concentration. Okay, and this table was then adopted by the FHW manual in August 1979. Then from the FHW manual, we adopted in our earlier 1993 manual. Okay, but in 2009, FHW deleted this table. Okay, and now after convincing in several minutes, now it has been removed from the 2009. So that's why now the coefficient of runoff, there is no honor, and now it's a function of the property of the soil itself. Okay, so this is a one of the area of the Thane, where the designs has been carried out by using the earlier CPHO manual. Okay, because this was already constructed in the Jawaharlal Nehru National Urban Renewal Mission in year 2009, 2010. So if you go by that concept, the time of concentration, if it's 20 or 20, 20, 30, the coefficient of runoff was 0.5, even if it's a paved area. Mind it, even if it's a paved area. And at the same time, the chainage, as per the chainage, if we proceed, because the time of concentration again is a function of the length, right? So mind it, if it's the upstream side, if it's chainage zero, the the coefficient of runoff of the same unpaved is a zero point 0.4, and if at the chainage in the downstream side, it's at the chainage at the 5,000 meters, right? For the same unpaved area, the coefficient of runoff is a 0.6. So that is the problem, right? Because of this varying coefficient of runoff for the same type of the soil or same plant cover, it has the under stormwater drain has been under designed. Okay, so this you understood why you frequently you're observing the flooding in the urban areas in spite of having new construction of the drains, right? This is because of the wrong design approach. So in a CPHU manual, they have specified for the central business and the commercial areas. So the class 1 cities, it's a 1 in 5 years. Then the industrial 1 in 5 year return period. Then urban residential is a 1 in 5 years. And the airports and other critical infrastructure, it should be designed for the 1 in 100 years, right? So this for the class 1 metro cities, and the class 2 is a different. So for your information, class 1 cities are the cities having the population of 1 lakh and above, and the other cities are having the population less than 1 lakh. Then if you see, of course, this is a compilation has been carried out by the Professor Kapil Gupta. So worldwide, let's understand what is a return period has been adopted worldwide, right? So if you see the European code advanced models, they use a 1 in 10 years, 1 in 20 years, 1 in 30 years, 1 in 50 years, right? In case of the Brazil almost same, 1 in 2 years, and the major systems is 1 in 50 or 1 in 100 years. So Japan is 1 in 10 years. So that's the main thing. That's why we try to push up. The professors try to push up. At least we should adapt the 1 in 5 years, and that's what's been adopted for NSC PHU manual. Okay, but the major infrastructures like a airport, like a Navi Mumbai airport has to be designed. And new greenfield projects, it has to be designed for 1 in 100 years. Right, there's a critical infrastructures. Even in the fact finding committee, they have mentioned the same. It should be designed for the 1 in 100 years. Okay, so accordingly, even I have been involved in a flood risk assessment of the various data centers. Right. So these data centers are very crucial, right? Because of the foreign fundings for the data centers and the foreign investors of the data centers in India, they do insist that the risk assessment should be carried for 1 in 100 years. So in that case, even in spite of, because I've been doing for the so many metro cities where the surrounding stormwater drain systems has been designed for 1 in 5 years or 1 in 2 years, right? But we have to design the internal. We have to do the assessment for 1 in 100 years plus the climate change and plus the tidal consideration, and for that we have to take measures, right? So this is a time of concentration. Then another lacuna in the old formula. Even now, what is happening? Because even now, I have seen some designs, okay, where they have adopted very improper formula for estimation of the time of concentration. And the time of concentration has the two components. That's the time of the overflow and the time of the flows, right? So that's the time of overflow. That's the time of inlet. Sorry, that's the time of inlet and time of the flow. So time of the flow is through the drain channel, and the time of initial inlet time is the initial time required for the stormwater runoff. Okay, to reach to the place, to reach into the drain. Now, this inlet time it's been changing over period of the time. Okay, for example, in case of this is the top case. The top case is a the inlet time is much more. Okay, and that's why we use the most famous formula. That's the Kirpish formula. Okay, and then what should be used if in case of the developed places, that's in townships and all, what formula should be used? That's again a question, right? Because if you see here, the time of concentration is 60 by the pre-development scenario, and because of the development, if the time of concentration is 60, the rainfall intensity is 50, right? And because of the development, the time of concentration is 30, and now the rainfall intensity is 70. So is it appropriate to use the same formula? That's the Kirpish formula, which is being used from several years of the time. Because why I'm mentioning all these things, because we do teach, because while in academics we do follow this formula, right? Okay, but there is another formula for the these urban areas, right? Which is mentioned only in the Venti Chow, and other books they have mentioned only this formula. So we should be while teaching to the students also, they should be aware that the students should also aware, no, there is a separate formula for the urban areas, right? So mind it, for all the stormwater drain which is being designed in the metro cities under the Jawaharlal Nehru National Urban Renewal Mission has been based on this particular formula. Even very recently, I've been to the Chennai for one of the project of the data center, and the designer has estimated the time of concentration based on this old formula, and the time of concentration was very high. So based on that, when he has designed the stormwater drain, so this is under design, right? So this is a very old Kirpish formula, and then for the urban area, they have suggested some constant, that's a multiplying factors, and very few books it has been mentioned. I've seen only in a vintage book. Okay, so actually it has to be reduced, right? So this is a proper formula, and Another because this is a function of the length and the slope. Then we have searched another formulas. We have done a lot of research in which formula should be used for estimation of the inlet time. Then we found one good formula in a Federal Aviation Administration manual, which is it's a US manual, and which has been used for the design of the airport permits, right. We have seen that this particular formula, which is a function of the coefficient of runoff, which is function of the length, and which is function of the slope. So this coefficient of runoff, it is very much important, right, while estimation of the inlet time. So we have this CPHU manual has adopted this particular formula, and now all the new designs has to be used this particular formula. Mind it, when we are teaching to our students, we have to teach based on this particular formula. Otherwise, because if their students are not aware of this particular formula, if they are not aware of the CPHU manual, then they will do the same mistake which has been done by our past designers, right? Then this is the intensity duration curve. This is plotted based on my own weather station. I have got a two weather station which is located on a rooftop of my building. Now they are earlier it was I used to download the data, but now they are I could not download the data because of configuration. But that time I developed this intensity duration curve, which clearly specifies for the 30 minutes its rainfall intensity is 80. Now, why I'm giving this particular curve? Because in urban areas, the time of concentration for the individual complex or the smaller projects is very hardly 10 minutes or 15 minutes. So that for that purpose, one we should use the very high rainfall intensity. Now, having said that, if you refer the design guidelines by the MCGM, they specify the 55 millimeter per hour rainfall intensity for the Mumbai. Now we have seen the so many historical rainfall data. So this 55 millimeter per hour is happening every event, right? So even 100 millimeter per hour is happening in at least twice or thrice in a year, right? So according to the rainfall intensity should be selected, right? So this is a rainfall intensity study for the one of the rain gauge of the Mumbai. So where we have seen the 15 minutes time of concentration, 15 minutes rainfall intensity is 111, 86, and 103. So based on this, our design, our rain system should be designed, right? So for the rainfall and runoff, the important for the planning urban drainage system should be how much the rainfall and the flooding, how much rainfall should be considered. Then what is the criteria and measurements. So measurements are the most of the cities, the measurements are neglected. We have to mean to see the measurements of the rainfall is neglected. Now let's understand. Okay, all the drains has been designed for under design, right? Now we have to suggest the mitigation measures. So mitigation measures are both the structural mitigation measures and non-structural mitigation measures. Now the structural mitigation measures are the cleaning of the nala, then the cleaning of the drain inlets, the provision of the adequate drain inlets, widening of the culverts, widening of the proposed nala and the tidal ingress areas. This we are carried out for the one particular nala in a Thane. The study has been carried out. So where we understood, okay, there is the earlier drains are not designed for the tidal ingress, right? And at the same time, they're under designed because of the wrong adoption of the coefficient of runoff and the lesser intensity because of the lesser return period, right? So what we did, so lower part, the end part, we have widened the downstream part of the nala, considering the flows from the tidal. Okay, so we have done the modeling, and accordingly the width of the channel has been widened. Okay, so this we're dealing with such case studies, we have to such areas, we have to do the actual modeling, considering the rainfall, they considering the tidal with the sea level rise, and then the according the width of the drain should be considered. But I've seen the so many designs where they have not at all taken into consideration the tidal. Okay, because they are not modeled in a proper sophisticated way. They are not modeled in the recent softwares, right? They're only the spreadsheets. Then the provision of the detention ponds and the holding ponds. So yes, if it is not possible to widen the drain, because it happened, right? Because it's already constructed, there's the building on the both side of the drain. Take a case of the Mumbai, take a case of Thane or any metro cities. So there is already a developed area, developed adjoining to the stormwater drains, right? So it is very difficult to widen. So in that case, what will happen? Okay, because the excess runoff, whatever happening has to be detained at the site, has to be hold at the site, right? Because you take a case of the simple example. So if it's a 8 units of water is happening, and if it's a what drain capacity of the drain is only of a 4 units, then this extra 4 units are resulting to the flooding, resulting to the water logging, right? So that peak 4 units has to be detained at the site, right? So there should be a provision of detention and holding ponds. Then installation of the tidal gates and the pumping station. Mumbai at several locations. They have already installed the pumping stations. Have already installed with the tidal gates and followed with the pumping stations. Then once you provide the tidal gates, it means you are preventing, you are not allowing the tidal water to get entered into the drains. But this tidal gates has to be complemented with the pumping stations, right? If pumping station, or there are two options, it has to be complemented with the pumping station where the space is not available to widen the drain. If there is a space to because what is happening, the tidal impact will be of a 4 hours or the 5 hours, right? At least for the 4 hours. Okay, so 4 hours. So the 4 hours, your tidal gates will remain closed, right? So once your tidal gates are remain closed, then whatever the water on the upstream side will get accumulated in the channel, right? So so for the 4 hours period, you have to provide a proper space for accumulation of the water. If the space is available, then you can combine with a holding ponds. Okay, if it is not, then the only option is remaining the pumping stations, right? So the huge pumps are provided in the Mumbai. There are several pumping stations at the Haji Ali, then the Gazdar Band, that's Irla, then there is a Cleveland Bandar, then the another two locations they have provided the pumping stations, right? So because of the pumping station, because of the tidal gates, it has helped in reducing the flooding frequency. Then the finalization of the formation labels for the undeveloped areas. This is very much important, right? Because of at so many places there are still lot of development will be happening, right? So this financial formation level has to be finalized considering the all the climate change impact. What are the two climate change impact? There is a rise in sea level and there is an increase in the rainfall intensity. Then the solid waste removal arrangement has to be properly provided. Let's take a case of the one area where there is a this is again one case of it was a live case which was referred to me for the design of the stormwater drain, design of the culverts, and how it should be done, and understand the impact of the solid waste, right? So if you see the figure, there's a lot of solid waste disposal under the culvert. This is again the below the culvert, right? So we have actually studied. It was for this we have worked out how much is a catchment area which is contributing this to this particular culvert. So this is a location of the culvert, and this we have model using the Haycross. I personally like the Haycross because it's a very good software, and it has been developed by US Army Corps of Engineers, and it's worldwide accepted software, right? So I've been using from last 10 years for various my projects. So this particular stretch was modeled by using the Haycross, and This is the upstream side, of course, and the water is flowing from this right to the left, and this is a blockage below the culvert, right? And because of the blockage, there is a rise in water level on the upstream areas, right? So this has been modeled how much there will be rise in water level. And if you see here, because of the removal of the blockage, there is drastically, if you see immediately below the culvert or immediately upstream the culvert. One sec. Yeah. So because of the removal of the blockages, there is drastically reduction in water level. Okay. So this is another the as a mitigation measures. We have to prevent the stormwater ingress of the solid waste into the channel, right? So this is how we can provide the screens um, inside the channel, so that all the solid waste uh, will get it will not enter into the drain, and this screen will take care of the solid waste, right? So this, of course, this drains system, this screen system, this of course has been designed by the uh, myself for one of the nala in Thane, right? So after the installation of the screens, lost of uh, lot of entry of the solid waste into the drain has been reduced. Okay. And then another is the type of the stormwater drain inlets. This is very much important. What how should be the designs of the inlet? Okay. Then the management of the pre and post development runoff from the disposal from the site. Okay. Now this is one of the case of the Mumbai, right? Where now you see here that Mumbai Drains, they have already designed for the 55 millimeter per hour. Okay, and this is a very special case where this is basically SRA project. So there in earlier there was a lot of open areas, and the pre-development runoff was not much, but after the development, because of the paved area, the lot of runoff has happened. So, okay, now we do understood, okay, because this increased runoff is increased because of the development, because of the post development, right? But this increased runoff, the external drains are not adequate to carry the runoff from this uh, development, this proposed development, right? Then what should be done? What should be done? Okay, then for that particular project, what we have decided, okay, the so this is the plot has been divided into sale and rehab. So the runoff from the sale component is collected in the collection tank, then the infiltration pit, and the roadside drain is remaining will go to the roadside drain. Then even from the rehab plot, rainwater will be collected in infiltration pit and the collection tank. And by this uh, so people before development, runoff is a 0.322 cubic meter per second, but after development the runoff is detained inside, and therefore there will be less impact on the roadside drain. So this kind of the study we have to do when there is any new development is happening in the urban areas. This is again the now if you understand that there is a uh, high intensity rainfall because of the climate change, and your drains are not designed for that, then what should be done? Then one of the measures as remedial measures, or even the external drains, external, because it happened, in case of the Mumbai nalas, or the Mumbai nalas are designed for the 55 millimeter per hour, and even the stormwater drains in the Thane, they have designed for the 50 or 75, right? Now, once you understand that the external drains are not adequate enough to carry the runoff which is generated because of the high intensity rainfall, then in that case you can suggest one can suggest the pervious concrete. Okay, so this is a very nice images of the pervious concrete. So the water will get infiltrated in the soil, and there will be less runoff disposal from the plot to the external stormwater drain. Then this is again the urban drain which is subjected to the uh, high tide, and let's see understand how it is being modeled. So this is a tidal. Let's understand the tidal impact, right? So water levels in the drain with the tidal impact is 1 p.m. Then there is a rise in water level because of the high tide. Then earlier it is a water level is 2.56. Then it is 2.86, then 2.89, and then again the low tide started, the water level started reducing. So this kind of the study we have to do to understand the impact on the tidal impact, of course, with the climate change. So with the climate change, what will happen with the climate change at the sea level rise? So because instead of this 2.86, it will be a point 3 plus. Okay, so accordingly we have to design the your inlet system. So let's understand this. So if this HFL is a high flood levels, and of course we have to take care that invert levels meeting the main drain should be at least above the HFL, right? So accordingly we have to so if this is a secondary drain, we have to understand what will be the water levels in the secondary drain, and accordingly we have to give the formation levels of the development, right? So these are the mitigation measure which has been already adopted for the Mithi River, and of course, it's this mitigation is a mitigation measures has beneficial in reducing the peak flow. So this is a inline detention system. There are two kind of the system. That's an inline and offline detention system. This I personally very like, has been again designed by Professor Kapil Gupta of the IIT Bombay. So this is located at the Babandaya on the Mithi River. So this is the left image is before that's at the time of the 26 July 2005. That's immediately after that, and after 2005, the several mitigation measures has been adopted, and the width of the drain has been before, which was a 20 meter. Now it has been widened to the 35 meters, right? So and they have provided this inline detention. Basically it's a weir inside the your channel. Okay. So this is a photograph. This is a one of during one of the monsoon days, and this is a during the non-rainy period. These are the wear, and this is a wear, and they have provided the orifice at the bottom. So dry weather flow will pass through the orifice, and once rains some more, it will this wall is acting as a wear. Okay, so this is a uh, photograph when it's during the heavy rainfall, and which was taken during the on the in year 2009, and this amount of the runoff is actually detained, and actually this help in reducing the peak. This is what is required in the urban scenario, because we have seen there is a double impact. There is double impact. Because there is not double impact. There are three impacts because of the under design, because of the high intensity rainfall, short term high intensity rainfall, and at the same time the tidal impact, right? And that to a sea level rise. So this kind of the system, if we implement wherever it is possible, this will be a help. It will be helpful in reducing the peak runoff. Then this is another case which I have studied for one of the areas in the Konkan areas, the Alibag area. So this is one of the plot where it is an open plot basically, and there is a existing tidal gate is located here, and it has been seen that there was used to happen that all these villages which is close to the plot and adjoining areas, they used to get flooded every year, and there was a lot of complaints, right? So and we did the hydraulic modeling of the this entire area and thing, and with the climate change impact, of course. Okay, so this is a one plot, big plot, and then this is a existing tidal gate, And because of the tidal gate, this of course this entire area was acting as a holding area, but it was water level, there is rise in water level, and because of this rise in water level, there are this village, it was entering into the adjoining villages, and there was a lot of complaints. Then we have done, we have studied the identified the different tidal gate. This is how we have to do, right? So by identifying the different tidal gate, there is a possibility of different tidal gate location. Now this particular area is acting as an additional holding area, and because of this, see, because of this, there is a very drastically reduction in the water level, right? And it has also absorbed the sea level rise. So this is because this is without this is with the existing tidal gate, and this is with a new tidal gate and with the additional holding areas. So this is how the holding areas has to be designed, right? Then the coastal flood mapping and the mitigation, because the coastal floods, why coastal floods? Because we have seen uh, there will rise in sea level in tune of zero point 0.6, 0.3 to 1 meter, right? Then we have to do the coastal flood mapping, and we have to plan for the mitigation measures. So let's understand one case. So there are two plots where we have studied what are the impact of the climate change and impact of the tidal. Climate change is both rise in rainfall intensity and the tidal and the sea level rise. Okay, so this is a why I'm giving up, because this kind of study we have to do for any particular project. So we have identified whether these different drain networks, stormwater drain networks. Then of course we studied the topography of the area and the adjoining areas, and these various the catchment sub-catchment areas which are contributing to the stormwater drain, and the secondary, of course, the primary and secondary drain. And then the tidal data, because we have to select the tidal data, and the tidal data is, of course, one can have a observed tidal data, and of course there are the tidal gates, tidal maritime Maharashtra Maritime Board, or they are publishing the tide levels data, so one can procure from the Mumbai Port Trust, as a Maharashtra Maritime Board uh, tidal data. And for your information, this is again, I would like, and always I will, as I say, explain, because there is again a huge gap in understanding. Okay, one thing is that all the tidal data are with reference to the chart data. So whatever the tidal levels which has been mentioned are with reference to the chart data. Mind, it is not with reference to the mean sea level, and this is where the engineers do the mistakes. Even the government officers, they do a mistake. Okay, because very in a very first page, on the very first back side of the page, they have mentioned that these levels are with reference to the chart data, and everyone is under the impression that these levels are with reference to the mean sea level. No, this is not. There is a difference between the chart datum levels, and there is a difference between the mean sea level. So it is our duty and responsibility of the designers that it has to be converted. The chart datum information has to be converted into the mean sea level. This is one thing. Again, in case of the Mumbai, all the levels in the Mumbai are explained in terms of the town hall data. Okay, though this is again a different scenario, different case, right? Because all the levels with reference to the town hall datum. So what does this town hall datum means? What is the equivalent sea level? So for the Mumbai, we do convert this town hall datum to the mean sea levels. So what is actually the mean sea level? Because this is what is creating a problem for the Mumbai city, right? Because MCGM do follow the town hall datum, okay, for the design, but we are not aware. Oh, what is, even developers or the local the designers are not aware. Oh, what is mean by the town hall datum? What is the actual mean sea level of that? So everywhere, all the levels, we have to be on the common platform, right? So this is what has been recommended in Brimstone report. So this is not Brimstone report. It has been recommended a fact-finding committee report. Fact-finding committee report is a separate committee which has been formed by under the chairmanship of the Chitle. So it is also referred as a Chitle committee report. This is for the understanding the reasons of the flooding after post 26 July 2005. Okay, where they have mentioned that all the levels should be at the one platform and should be on the one with reference to the mean sea level, and whether it has a chart datum or it has it's a town hall datum, it has to be converted in the one platform that with reference to the mean sea level. Okay, then again we have to understand the daily maximum rainfall for any particular area. Then of course short-term rainfall, that's a rainfall intensity for the time of concentration of the 10 minutes or 15 minutes or the 30 minutes we have to understand. And then we have to do the design, right? So this is a catchment contributing the stormwater drain. Then we have actually understood the plot topography. So this is the pre-development scenario. Then this is 3D view of the plot, and then again we have estimated water spread. That's a high tide level of a 2-meter MSL and the rainfall intensity of 100 millimeter per hour, and the simulated water level is 2.95. Okay, so this is a plot, and this is what will be the water level in the plot. Okay, and this is again we have one thing is much more important, that whatever the models gives, that has to be calibrated. The model has to be calibrated, and of course this when we carried out this study, the model was calibrated with a known observed one. Then this is a plot topography, this post development, and this, if you see here, this is a pre-development, and the right hand side is a post development. So we have to understand the present topography, and how the plot will change. And of course when we do the why we do all this study, because if there is a particular development in the plot, if we are elevating the plot. Okay, understood. Now if there is a climate change impact, if the sea level rise, okay, I'm raising my plot, but okay, you are raising your plot, but what about the adjoining area plot, right? So we have to take care of the adjoining areas as well, right? Then the water, then we have to provide the internal stormwater drain accordingly, so that adjoining water levels from the adjoining areas can be taken care, can be disposed of. So this is again a 3D view. This is a post development, this is a pre-development, and the post development. Fine. So this is again a 3D schematic. So this is how we should be planning, right? This is how we should be doing, rather than designing the stormwater drain into the Excel spreadsheets, right? So we have to come out from the Excel spreadsheets. We have to actually train our engineers to do the modeling like this. So considering the tidal impact, considering the tidal impact, considering the sea level rise impact, and the rise in sea level. Okay. Then the plot formation levels. So based on this, we do suggest the plot formation level. Another thing is that see, one, I have explained that there is a sea level rise. Okay, sea level rise. So accordingly, we have to consider what about the climate change? What about the high intensity rainfall? Right. So there is an international practice which we do follow for our projects. Right. So as per the international practice for climate change, with respect to the intensity of the rainfall, we have to adopt the 20% uplift factor. What I mean to say, that we have to increase the rainfall intensity by 20%. Okay, suppose for now for 1 in 5 years return period, if the rainfall intensity is 100, then we have to adopt the 20% more. That it means we have to design our system for 120 millimeter per hour. This is what we are doing, right? Even in the case of the Thane, the time of concentration, for the time of concentration of 10 minutes. This is let's see if there is somewhere. So this I will explain with this particular figure. So for the 5 minutes time of concentration, so rainfall intensity is 120 millimeter per hour. With the uplift factor of the 20% climate change, the design peak rainfall intensity is becomes a 144. So you can say it's a 150 millimeter per hour. But if in the time of concentration is a 25 minutes, which is normally happening in the urban areas, so rainfall intensity is around 80 millimeter per hour. With the uplift factor of the 20%, then at least rainfall intensity becomes the 100. So at least the urban areas should be designed at least for the 100. At least when I talk about the urban area, and here this is case is only for the Mumbai, but at least it should be designed for the 100 millimeter per hour. But again, there are certain new things. But 1 in 5 years return period time of concentration for the Santana cruise is a 96.44. Then you can adopt the 20% more. So what I'll recommend. So for your own areas, you should try to find out the IDF codes for own areas, and accordingly you should increase the rainfall intensity for the design purpose. Okay. So this is let's understand the flood mitigation measure, the non-structural flood mitigation measures. Then these are the real-time rainfall monitoring and alert systems. Then real-time drain river water monitoring and alert system, the real-time tidal water level monitoring and alert systems, and demarcation of the high tide and flood levels. Okay. Now, for your information, let's take one by one. So Mumbai, this real-time rainfall information, which after 2006-2005, because of the initiative of the Professor Kapil Gupta, Mumbai has installed the rain gauge at several locations, and which is active since then. Even if you see the present Mumbai monsoon and even MCGM website, you will find the real-time rainfall information on their website, where they do provide the rainfall information from the last 10 minutes, 15 minutes, 30 minutes, 1 hour. Okay. So this is and what will be helpful. And one thing what they have said, because since the Mumbai system has been designed for the 55, so they have set an alarm that if it's 15 minutes, if rainfall happens 10 millimeter in 15 minutes, which is equivalent to the 40 millimeter per hour, then they will send a message system. Okay. So alert. There will be alert, internal alert, and that alert will be sent to the disaster to the city managers, right? So this is one. Then, as a part of my PhD, I had developed a methodology for real-time flood warning systems. Okay, and this actually it was implemented at that time itself when I was doing my PhD, and it was implemented for the Thane as internally, and of course I studied for the Methi River, right? And then there are two components. Okay, then the model development and the model application. Of course, when I am talking about the real-time flood warning systems, there are it has also included the real-time rainfall data, real-time rainfall monitor, rainfall estimation, right, and forecasting. So for that, I use the SVM rainfall forecast model. I use the SVM tool for forecasting the rainfall, and with that forecasting tool, it was possible to forecast rainfall 20 minutes ahead. This is one. Okay. And then in case of the 20 minutes ahead rainfall forecast information was available, can be made available from the rainfall forecast model, whether it can be SVM, neural network, or any. But I have used the SVM. Okay. Then for the rainfall runoff course, I have used the recorded rainfall events, the catchment characteristics. They use the HMS software and the catchment. We're using the HMS software. We estimated the catchment runoff, and based on the catchment runoff, rainfall runoff curves were developed. And this computed or simulated runoff was used as an input for the HECRAS along with the river geometry, and the water levels were estimated. Okay, and water based on the water level, the depth discharge curves were developed. Okay, so once I know the rainfall, I can we can estimate the runoff based on the rainfall runoff curves, right? And this runoff as an input to the depth discharge curve, which was developed by using the HECRAS. Okay, once I know the runoff, I can estimate the depth. So this is very simple real-time model which was developed. And once I know the water level, then we can issue the flood warnings and the flood alert systems. So this then we can have a alert dissemination system such as communication to the municipalities, then the transport authorities, then the mass media, and the citizen using email, SMS, and the mobile app. Okay. So this was my case study I carried out on the Meteor River. So we considered the entire catchment area, and the head is the Heck HMS River Basin, Hekras River Geometry. Then of course there was a this is the Kantinagar area. We had this gauge at the Kantinagar location where the MCGM people they used to observe the water level. And mind it, at that time they have deputed one special person which used to sit in a shift basis 24 by 7. Okay, and so for one particular event we had the observed water level, and based on that we developed the model. Okay, so this is the interface which was developed by me for a real-time interface. So once I know the uh, rainfall for last 1 hour rainfall, we can estimate the rainfall 20 minutes side rainfall, right? So once the models are calibrated, it has been taken the 5 minutes to run the simulation. And since the time of concentration is a 30 minutes, and lead time for the rainfall was a 20 minutes. So total the 30 minutes time of concentration. What mean time of concentration means 30 minutes ahead we can estimate the water levels. So this 30 minutes time of concentration lead time and 20 minutes lead time in a rainfall forecast. Total lead time was 50 minutes, and 5 minutes for the processing the data. So 45 minutes lead time was available with this method. Of course, this is very short term alert, but for the urban area, since the time of concentration is less, 30 minutes. This is really helpful in evacuation and relief. Okay. This is the actual photographs of screenshot of the model where this is a water level, and this is a where the input is from the rain gauge, whatever the rain gauge, and different scenarios we have put. Okay. So this is a real time the flood forecast model, and based on that, of course, I have developed last year. We implemented a project for the Thane, which I covered after some slides. Okay. Then the rapid flood risk assessment of the Mumbai. I was involved in the rapid flood risk assessment. So where we have developed a flood spread map for the 50 millimeters and 100 millimeters per hour. Rainfall intensity of the 50 and 100 millimeters per hour. So these are the objective of the study is that, okay, once you understand the flood spread and the population affected for the different rainfall intensities, so it will help in city managers, disaster managers to plan the mitigation plans, to plan the rescue measures during the flood event. Then based on my PhD research work and the whatever the implemented real-time implementation of that time, based on the rain gauge which was installed on rooftop of my building, then we developed a real-time flood warning system for the Thane, and it's online now. Of course, it's not for the public openly now, because uh, this year they want to keep for the city managers, and I hope from next year's, actually it was supposed to keep make it open for the public this year, but they have decided, okay, for this year they will be for the city manager. From the next year onwards, the real time flood warning system will be open to public. Okay. So we for that we have studied the stormwater drain networks of the entire Thane. Then we have identified the catchment areas which is contributing to the different nalas. So this is for they have identified the nalas 1 and 2, then 3, then 4 and 5, then the Parsik, then the catchment contributing to the Mumbra Diva, and then this is a particular catchment area which is contributing to the Thane Creek. Then in Thane, if you see, there are two. This is a Thane city which is divided into the two by the Thane Creek. This is main proper Thane city. This is a Gorbanda area. This is a Kalwa, Mumbra. This is a Kalwa. This is a Mumbra, and this is Diva area. Okay, so there are two main water bodies. This is the Thane Creek and Ullas River estuary. So we have studied the both water bodies. Okay, so these are the catchment area which is contributing to the Thane Creek. This is the catchment area which is contributing to the Ullas River estuary. And then for the simple understanding, this is a low tide without a rainfall. This is a low tide with a rainfall. Okay, and this is a high tide without rainfall, and this is a high tide with a rainfall. This is the impact, right? So we have studied the rainfall and the tidal analysis. And this is for one particular nala, we have done the model to understand the impact of the tidal. So this is a water level with 100 millimeter without tide for the 100 millimeter per hour rainfall intensity, and with the tide there is a rise in water level. So this because when we are developing the real time model, this kind of study we have to do. Okay, because for the forecasting of the water levels. Then again these are the high tide scenario with a rainfall. This is rainfall intensity in the high tide scenario, and then again this is a high rise in water level because of the Ullas River, because of overflow of the dam. This again we have to add into the scenario. But basically, when we are doing the real time flood forecast model, this is very site specific. It's very location specific. For an example, when we develop a real time flood forecast model for the Mumbai, that is for the Methi River, then we have also studied the overflows from the dam. That is a different scenario. That's a without overflow of the and there are two lakes, right? One is the Powai Lake and another is the Vihar Lake. So first is one scenario is without overflow from the lakes, without tide. Then without overflow from the lakes and with tide. Then the another scenarios is overflow from the Powai Lake. Then because Powai Lake overflows when the annual rainfall is around 500 to 550 millimeter. Okay, and after that Powai Vihar Lake overflows, and Vihar Lake overflows around almost when the annual rainfall exceeds 1,000 or 1,000 or 1,100, depends upon the what is the how much is the water level in a lake. But these are rough figures. And after that, of course, the Bihar and then we have to consider this when we are developing the real time flood forecast model for the Thane. We had to consider the Ullas River overflows, right, for developing of the model. And this is for the 50 millimeters, and then this is a high tide with a 50 millimeter water level in Ullas River. So these are the combinations of the different uh, rainfall intensities for the 100 millimeter per hour, right? And then once we understood the what will be the water level for the different rainfall intensities considering the tidal impact, okay, then this is architecture, right? So Thane Creek real time water level monitoring system. So we have installed the real time water level monitoring systems, okay, at various locations. I will show you on the okay. I will explain on the figure. Okay, fine. Okay, so this is a Thane Creek installed a real-time water level monitoring system, water level sensor at this particular location for the Thane Creek, and we have installed for the Ulas River estuary, we have installed one at the Gaimuk, because during the high tide, water will be entering from the Vasai Creek, right? Vasai Basin, and another water level sensor we have installed at near the Mumbai. So we to understand, because this is upstream of the city boundary. So to understand what will the impact of the overflows of the dam, okay, in Ullas River, okay. And last year we actually monitored when there was a flooding, happened in the Badlapur. In fact, I was traveling to the Konkan area, and actually I was live monitoring while traveling itself. I was monitoring, and when I saw that, okay, during the afternoon, there is certain rise in water level in Mumbai. So I was surprised why this is happening. And when we halted at one particular place while traveling, then I understood. Oh, then I saw the news that there is a lot of flooding happening in the Badlapur, right? So this impact. So once if I know that this water is entering because of overflow of the dam, overflow of the dam, overflow of the dam. So we can take a measures, right? Because this is a proper strategic location from where water will be entering the Diva and water will be entering the Mumbai. And for your information, entire Diva is its low line area. So average mean sea level is a 3 to 3.5. So that's why strategically we have located the water level sensor at this particular location, right? Another thing is that so this actually helped in understanding, even for the city managers. Oh, okay, look, now the water level is rising and we have to take care, because why we did all this exercise, why we installed, because for information, the tidal data is available at the 6 hour intervals, okay. That is low tide, high tide, low tide, high tide. What about the levels in between? And that the tide levels information is a calculated, is an estimation. It's an estimation because of the old records. Okay, so that may not be a realistic. It is fairly matches up, because again the tide level is based on the one calibrated data, okay, at one particular place, and accordingly they have simulated the model, and they have estimated water levels at different locations. Okay, but for the urban area, there has to be some mechanism to understand what is the real-time water levels. So that city managers, because if the rain is happening, if we take a case now, if it's now it's a heavy rainfall, so one should not be in a panic position. If his rain is happening, if I know what is the current tide level, oh, it's a low tide, no need to panic. Even it's a low tide, between the low tide and high tide, oh, this is a 2 meter MSL, oh, I should take care. Oh, it's a 0.5 MSL, I no need to take care. Okay, so this is that's why this information is really helpful while planning, while deciding the mitigation measures, and while deciding the rescue measures, right? Then apart from that, we have installed the real-time water level sensors for the two of the nalas, or three of the nalas. One for the one near the Thana College, another is at one Vrindavan, and another is near the Hiranandan Estate. So mind it, the purpose of installation at in the nalas, to understand the impact from the upstream areas into the nala. Okay, so that we can give the alerts to the downstream areas. Okay, this is the one. Another thing is that then, based on this information, we have actually modeled one of the nala. Okay, and based on that model, we are giving the present water levels and the forecasted water levels. Because mind it, it is very much costly affair to install the real-time water level sensor for all the nalas, right? It will be very costly affair. But it has been done by the Kolkata. There's been by the another local authorities, right? Mumbai, I don't think they have a real-time water level sensors, right? But since it's a costly, because every city wants a cost-effective solution. So that's why the real-time modeling part will be really helpful in estimation of the water levels. Okay, so that's what we did. The combination of the modeling, that's a forecasting system, and the existing and the live real-time water levels working. So this is okay. So the water levels information will be coming from the sensors from the both Ullas River and Thane Creek, and the rainfall information will be coming from the real-time automatic weather station. And this real-time information, along with the real-time water level information or the tidal information, will be helpful in forecasting the water levels. Okay, and then the forecasted water levels will be sent to the for the disaster manager. Of course, we have set the various levels of the warnings based on the tide levels, based on the localized water levels, and at the same time, if the rainfall exceeds 12.5 millimeter per hour in 15 minutes, we do send the alerts. That is if its rainfall exceeds 50 millimeter per hour. So this kind of the rainfall alert system and the water level alert system has been developed for the Mumbai, for the Thane, and which is been active, which is been online, but is not for the public, for the city managers. And this, of course, this particular project was sponsored by ICLEI. It was sponsored by UN Habitat and European Union. Right. So this was a sponsored project, and this my product, my baby, we have given the name of the Tufan. Right. It's a Thane Urban Flood Alert Network. So that's a Tufan. So it's a basically then now it has become a uh, it is of course, and this model was developed as a part of the study which has been carried by the ICLEI for the climate to make the city as a climate resilience. So it is the best pilot study, and this has been recognized by various levels. That is the best pilot study for this is one of the step for making the city climate resilience, because once you know the impact of the flooding, and you can plan, and even either you can estimate what is the high impact of the rainfall. Okay. Then this is the Barcelona detention pond.
Each tank controls a specific area of water catchment and regulates its flow toward the area that it serves. The regulating tank at the Escuela Industrial lays beneath a football field. It has a total storage capacity of 35,000 cubic meters, the equivalent of 10 Olympic-sized swimming pools. With a rectangular ground plan, its walls are 7 meters high. It serves the entire area of the Avenida de Roma, Ucegel, Parallel, and Rabat. As with the rest of the tanks, it has a local control center. The water used for cleaning the tank comes from the water table. The Zona Universitaria regulating tank is the largest in Barcelona and the second largest in Europe. Its specific purpose is to regulate the flow of
The first, what we have seen, the football field, they have converted the area below the football field as a holding pond, and this is a very good example where the car parking areas with below the area were converted into the very huge holding pond. And I feel this is a requirement for the urban areas. This is required for Mumbai areas. This is required for the coastal areas to mitigate the climate change impact.
122 meters each, with a maximum depth of 11.5 meters. Among other functions, the local control center regulates the cleaning of the tank with water from the Barcelona subsoil. It serves the labels and a depth of filling capacity to alleviate.
This is again another example of the.
Universitaria tank.
So similarly, we can identify, of course, while doing the study, we have identified the Mumbai's and even the Saint Javier
Its
Garden.
volume is 52,500 cubic meters, the same as that of 18 Olympic swimming pools, and its walls reach a height of 20 meters. The local control center regulates all of the tank's functions. The Parque Juan Lido regulating tank 1,000 cubic meters, equal to 20 Olympic swimming pools, and has a depth of 17 meters. Its primary function is to regulate water funneled off Tarragona Street, thereby reducing the system's load in the area of Gran Via, Paseo de la Zona Franca, Diputación, and Ciudad Bella. Due to that of over 100 Olympic-sized swimming pools. By the time the storm hits, the city
So this what we have seen in the video. Thanks to Professor Kapil Gupta for sharing the video for this presentation. Because he has been to the Barcelona, he has seen all these systems, and that's why he has taken the photograph video. Okay, so even for the Mumbai, we require this kind of the detention of the holding ponds. Of course, Mumbai have initiated. They have provided already holding tanks at the two places. One is near the Ville Parle, another is at Saint Javier ground. So Saint Javier ground again, they are augmented with a few additional pumps. So this kind of the system is required to take care of the climate change impact, whether it is a rise in sea level by 30 centimeters or 60 centimeters, because it is a very, very alarming, and at the same time increased rainfall intensity, short-term rainfall intensity. So these are the National Disaster Management Guidelines, which is, and my Professor Kapil was a co-convener of these particular guidelines, and these are the four snapshot of the stormwater manual, which is published by the CPHU in 2019. So thanks a lot for patient hearing. The floor is open to the questions. Of course, any questions, any queries, open. Of course, few minutes left.
Yes, sir.
Yeah.
Thank you, sir, for such an informative session. We have some questions in YouTube chat box. Can we proceed, sir?
Yes.
Okay. Sir, first question from Professor Megadatta ma'am. Which software you are using for analysis and plot the topography?
Yeah, there are several softwares are there. So I have been using the ArcGIS for the analysis purpose.
Okay. Second question from Professor MP Joshi sir. Each sponge city concept prove usually for flood mitigation measures?
Sorry, what was the question? Pond city.
Sponge, SPONG.
Yes, definitely. Definitely. Yeah.
Okay. Next question from Professor Abhijit Kamte sir. How to overcome the situation of flood in areas like Dhadavir?
Yeah, Dharavi, for example, they are planning for another tidal gates, and they are also planning for the pumping station. Okay, because Dharavi is already a low-lying area, so that's why what is their plan? That's to provide the tidal gates, and at the same time, because I have been studying the adjoining areas, they are also planning for increasing the drain width. So there's it's a combination of the increasing the drain width, there's a nala width, and at the same time the tidal gates.
Okay. Next question from the student, Mr. Vipul Survey. Sir, can we use the permeable concrete in Maharashtra currently?
Yes, you can use. It's better. I've been recommending for so many projects, especially data center projects, that they should be using the Pervious Concrete.
Okay.
So yeah, the speaker of Vijay Kulkarni is very much expert. Who will be giving the talk on day before, on Wednesday, I think Wednesday or Thursday.
Yes.
So he's very much expert. He's a concrete expert, and he will guide you. Yeah.
Okay. Okay. Thank you, sir. Here question answer
Thank
session
you.
is over. Participant, here I end this day one of session two. Feedback form will be provided on your registered email ID, so we can meet for day two, 10:30 a.m. on tomorrow.